Hi, good morning or good afternoon. I'm Naoki Mizukami, hydrologist at the National Center for Atmospheric Research. So today I'm talking how CMIP data is used to hydrologic system vulnerability assessment. I'm going to focus on US, Canada, mostly US Pacific Northwest area. So project team consists of few different agencies, institutions, mostly divided into a scientific institution and then water resources agencies, and then University of Washington at the NCAR here. Two groups of more scientists producing a lot of simulations and data sets for practitioner, which is end user, which is Army Corps of Engineer, and then sometimes we work with U.S. Bureau of Reclamations. So those are end user for to provide data. So a little bit background of Pacific Northwest. So hydrology in Pacific Northwest is driven by most winter atmospheric river, which coming from Pacific. You can see one example, 2007. And then this is the radar estimate of November rainfall from November 28th to December 2007. You can see a red bulb in the Pacific Northwest coast. So this produced huge rainfall. You can see even in the winter, you can see a spike in the stream flow observations. I'm showing this is observation and then simulation to the one sites, and the map is here. This caused flooding, and then a New York Times took a reported this event, which called like a Great Coastal Gale of 2007. So this happened often, and then this atmospheric river, we don't know what's gonna be in the future in changing climate. In the meantime, Pacific Northwest area, especially at the Columbia River, which is a big river system, has about 250 reservoirs across the river system, managed by federal agencies and then sometimes private entities. So people, water resources manager, always looking into how they can assess vulnerability for reservoir given the climate change. So they ask sometimes scientists to produce historical future stream flow data sets based on updated process-based model, particularly useful for reservoir assessments. And this is how we do usually. So here comes CMIP data. We start with CMIP data. Here's a question: how we can select GCM outputs, because there's hundreds combined, like a scenario, several scenarios, and then GCMs. We're sometimes facing like hundreds of GCM outputs, and then we can't process all of them, so we have to select somehow. And then GCM data outputs is cost for hydrologic modeling. So we use downscaling, spatial downscaling. There's two choices: statistical based and then more physical based, dynamical. But dynamical is so expensive, so we cannot do multiple GCM output downscaling. So in the past, typically people use a statistical method, so we can do quick. And then finally, we can run the hydrologic model, but hydrologic model is sometimes not accurate. So we have to spend a lot of time on the parameter estimation, and then sometimes update hydrologic model too. And then finally, the data sets produced by hydrologic output from hydrologic model is delivered to end user, so they can do risk and impact assessments. So this is what we use for climate impact modeling chain. Red box is kind of new data and then technique as of 2022 when we started. And one thing we want to highlight is downscaling method. So we did not use a statistical method, which people tend to use it, but we did not use even dynamical. So we used, it's called ICAR, Intermediate Complexity Atmospheric Research. This is a simplified weather model. So that has some physics-based weather model. So and the output is more based on a process-based, but it's greatly simplified compared to a regular weather model like WRF. And then we updated hydrologic model. It's called SUMA, and then Mizroute. SUMA is land surface model, and then Mizroute is river model. And then we did some bias correction. We're not talking today, but mostly focusing on this area. So this is just the same information, but the more graphical slides. So CMIP 5, and we use CMIP 5 and 6, which is 50 to 100 kilometer grid. And so we did ICA downscaling to 6 kilometer scale, and then we remapped to SUMA hydrologic model spatial element, which is catchment. We use catchment-based model, so we can see what that looks like here. The color is elevation, so we like run a hydrologic model like almost 10,000 catchments. And the river model is a little bit higher resolutions, so we have 18,000 river reaches, so where like we estimate stream flows. So I'd like to just talk about a little bit calibrations and then evaluation. Just step away from CMIP, but this is most we spend a lot of time on. So I just wanted to show some of the results. And so how we hydrologic model calibration is very challenging. So we luckily have a naturalized daily flow. By the way, we try to estimate like a natural stream flow not impacted by lake and dam, which is kind of a counterintuitive because they're doing a reservoir assessment, but the agency is looking for natural daily flow simulations. So we have luckily naturalized daily flow, so we can calibrate hydrologic model SUMA. So how we selected 65 sites at the natural flow sites, and then calibrate SUMA for each element catchments. And then once you've done a headwater basins, we're marching down to downstream one by one. So in the end, we adjusting parameter for most of Pacific Northwest domain, and then a couple of areas, closed basin, they don't really care much, so we didn't calibrate. So this is more detailed, but I just wanted to highlight we have observation-based climate, the forcing too, from about 30, 40 years. So we can use this is forcing to calibrate and evaluate hydrologic model. So this is just a highlight of evaluations. So left SUMA is our model, new model, and then big P1 is old previous study for these areas, Teguidin et al. 2019. If you have you can look at the paper. So just comparing side by side. And then looking at here, KGE, which KGE, we use KGE, hydrologists use KGE a lot, but this is just a metric, skill score metrics. And then one is perfect match of the observation time series. And then as you go, skill score is lower, scale worse. So you can see some of blue high scores, and then mostly you can see a similar pattern, even independently calibrated and then simulated. So this is just a direct comparison side by side, each sites, and then you can see a lot of blue, which is current SUMA model is better than old big simulations. And I just wanted to highlight some of our areas where we cannot simulate good, which is the Deschutes River, and a red highlight circled because of a groundwater recharging to river. So both models Suman and BIC do not have groundwater in the model, so both models are struggling. But in the end, we are happy with this, so we move on. Okay, so another thing we looked at the high flow bias because agencies sometimes needed this information correctly. So here we do what we do. So this is just a cold flow duration curve. So basically, if you have a time series, daily time series number of year, and then sorting from high to end, and then plotting like a non-exceedance, like an empirical probability versus sorted stream flow. And if you look at the 0.9 or above, this is high flow regions, and then comparing observations. And then we repeating other sites. And then if you look at the PDF, SUMA improved the big simulations. So we are happy with this too. And then another thing we did is, okay, if calibrated model is forced by GCM actually forcing in the historical at what the error matrix looks like. So from top, it's just a bias. So this is just a ratio observation to simulation. So 1 is good. And then variability ratio is also a temporal variability of simulation to observed variability. So 1 is perfect. And then the bottom two percentage bias of high flow, and then like the bottom is low flow. And then you can see and then CMIP 5 and then 6 forced runs are blue, and then GMET. This is observation based runs, calibration used for forcing used for calibration. So we wanted to see a consistent error pattern across the forcing. So we are happy with this. So now moving into like a hydrologic projections. So I cannot show everything, but so this is just a few highlights from historical GCM runs and how they change in the future. So this is showing 80 to 2004 mean annual flux from precipitation, ET instantaneous runoff, and annual max snowwater equivalent. And this is just using CMIP 6 ensemble. And then also I'm showing this is a stream flow final product. It's showing annual max flow, high flow, and how these are change in the future. And then this is looking at the end of 20 years of end of 21st century. And you can see most of the flux that actually increase. And then this is just showing, I think it's a high emission scenario. So it's more high side of a change. And yes, so in the end, it's annual max flow. Even annual flow is increasing in the future if you take a high emission scenario. And then looking at the particular sites where US Army Corps is focusing on, this is one Libby Dam at the interior of Colombia. And then this is showing annual mean flow change time series. I'm showing just a lot of lines. Historical has like a GCM historical runs, and then naturalized observation flow, and also GCM observation based forcing runs. And then future is low emissions and then high emissions. And then bottom plots the annual cycle. And then you can see in the future early stream flow, timing, peak flow, and then also increasing. And then you can see how low emission scenario and high emission scenario different. And then another sites, this is coastal sites, which is different seasonal cycle in the stream flow because of sometimes rainfall happens in the midwinter too because of warm moisture coming in. And then in the future, it's also similar to interior. It's more increased stream flow expected. So the summary, so stakeholder and then practitioner always want to update vulnerability assessment for dam and then reservoir. And then given new climate information available and then new technique for downscaling and then hydrologic modeling. And then here we produced CMIP-based Pacific Northwest hydroclimate data sets. And then it's more detailed. We have submitted paper to scientific data. And then data set is also available at these sites. If you are working on, want to do some study in the Pacific Northwest, it will be our data is available, and then we direct to always hear feedback. And this is final in the US, and tomorrow is Thanksgiving. Everybody is now gone. So here's my final slide.
Okay, thank you, Naoki. Thank you very much for that.
Yes.
Is there any questions from anybody in there? I don't see any hands up, but I did have a quick question myself. Will you update this your model to make use of CMIP 7 data once that becomes available?
Yes, always. Yes, agency is looking into new CMIP data sets. Yes.
Just another quick question that I thought about was this is obviously to a specific catchment, but could you apply this technique, like your model, to other catchments, say in the US, or does it only work with this local catchment in Pacific Northwest?
So in the US, most of study this like a regional domain is Pacific Northwest or Colorado River, which is a big, interesting or important basin. But we are doing actually entire corners for similar to this, still in progress. I think in a few months ago, Andy Wood presented something like this in a CMIP seminar.